A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
Imagine you are a commander in a high-intensity conflict. You have a sophisticated radar array on a hilltop and an interceptor battery in the valley, and they need to talk to each other with sub-millisecond latency to catch a maneuvering target. Usually, you would rely on a buried fiber optic cable for that kind of bandwidth, but then a cruise missile hits a junction box or a sabotage team digs up a trunk line, and suddenly your multi-billion-dollar defense system is blind and mute. Today's prompt from Daniel is about the invisible alternative that is currently keeping the lights on for command and control networks in the Middle East, specifically military microwave backhaul, or what some people call fiber in the sky.
It is the ultimate hidden backbone, corn. I am Herman Poppleberry, and I have been diving into the engineering specs of these systems because they are often the forgotten middle child of military communications. People talk about Starlink and satellite constellations, or they talk about tactical radios, but the high-capacity microwave links that bridge the gap between fixed infrastructure and mobile units are what actually carry the heavy lifting of modern sensor fusion. We are talking about the literal nervous system of the battlefield.
It is funny because when we think of microwave, most people probably think of those big drums on top of old cell towers, or maybe their kitchen appliance. But Daniel is pointing us toward a much more hardened, high-stakes application. In civilian life, we have seen this used to connect hospitals or remote campuses, where digging a trench for fiber is too expensive or slow. But in a war zone, the calculation changes from cost-saving to survival. Why is this suddenly the preferred redundancy for command and control?
The shift comes down to two things, capacity and deployment speed. For a long time, microwave was seen as the lower bandwidth option, something you used when you could not get fiber. But with the advent of E-band and V-band technology, which operate in the 70 to 80 gigahertz range, we are now seeing wireless links that can push 10 gigabits per second over several kilometers. That is fiber-level speed without the vulnerability of a physical cable. If you are the Israeli Defense Forces operating in the north against Hezbollah or preparing for long-range engagements with Iran, you cannot wait 6 months to permit and lay a hardened fiber line through mountainous terrain that is actively being shelled. You can, however, put a microwave dish on a telescopic mast or a hardened concrete tower in an afternoon.
And if that tower gets hit, you are just replacing a dish and a mast, not trying to find a break in 5 miles of buried glass while under fire. But I want to push on the reliability aspect because that seems like the Achilles heel here. We have all had our satellite television cut out during a heavy rainstorm. If you're running the Arrow missile defense system or an Iron Dome battery, you cannot exactly tell the incoming barrage to wait for the clouds to clear. How do you make a wireless link mission critical when physics wants to get in the way?
That is the core engineering challenge, and the solution is something called adaptive coding and modulation, or ACM. In a perfect sunny day, the system might be running at a very high complexity, like 4096 QAM, which allows for that 10 gigabit throughput. But as soon as the sensors detect atmospheric attenuation, like heavy rain or even thick dust from an explosion, the system automatically and instantaneously scales back. It might drop down to a simpler modulation that only provides 500 megabits per second, but the link remains rock solid. It chooses a slightly slower, more robust connection over a fast, fragile one.
So it is like a car that automatically shifts into a lower gear when it hits a steep hill. You might not be going 100 miles an hour anymore, but you are not going to stall out. But even at 500 megabits, that is still plenty of overhead for the kind of telemetry data we are talking about for missile defense, right?
More than enough. A radar track for an incoming projectile is actually a relatively small amount of data in terms of raw bits, but it requires extreme consistency. What kills a command and control network is not necessarily a drop in total bandwidth, but jitter and latency spikes. If the packet telling the interceptor where to move arrives 3 milliseconds late because the network was struggling with a rain cell, that interceptor might miss by 50 meters. These military-grade microwave systems are designed with hardware-level prioritization. They treat the command and control data as the absolute king of the pipe, shoving everything else aside to ensure that specific stream stays at a constant, predictable latency.
You mentioned the E-band at 70 and 80 gigahertz. For the non-engineers listening, why does the frequency matter so much here? I assume there is a trade-off between how much data you can carry and how far that signal actually goes.
You hit the nail on the head. Higher frequencies allow for much wider channels, which means more data. It is like having a 20-lane highway instead of a 2-lane road. However, high-frequency waves are very short, which means they are easily absorbed by the atmosphere, specifically by oxygen and water molecules. This is why E-band links are usually limited to maybe 3 to 5 kilometers if you want high availability. If you need to go further, say 20 or 30 kilometers, you have to drop down to lower frequencies like 11 or 18 gigahertz. The military uses a layered approach. They will have a long-distance 18 gigahertz link as the primary backbone, and then short-range, ultra-high capacity E-band links for the last mile to the actual battery or radar unit.
It creates this sort of invisible mesh over the landscape. I was looking at some open source intelligence reports recently about mass construction in the Galilee and the Golan Heights. You see these very specific clusters of directional dishes. They are not like cell towers that broadcast in every direction. They are pointed very precisely at another node. It seems like that would make them much harder to jam than traditional radio, because you would have to be standing almost exactly in the line of sight to interfere with the beam.
That is a huge security advantage. Traditional military radio is often omnidirectional, meaning it spills signal everywhere, which is like shouting in a dark room. Anyone with a receiver can hear you, and anyone with a jammer can drown you out. A microwave link is more like a laser pointer. The beam is incredibly narrow, often only a few degrees wide. To jam it effectively, an adversary like Iran or Hezbollah would need to place a jamming platform directly between the two towers or very close to the receiving dish. That is physically difficult to do when those towers are located on protected high ground or behind friendly lines.
And I imagine the electronic warfare aspect goes both ways. If the beam is narrow, it is also much harder for the enemy to detect that the link even exists unless they happen to cross the path of the beam. It is a form of low probability of detection. But what happens when we talk about the 2025 and 2026 conflict dynamics we have seen? We saw those massive saturation attacks where hundreds of drones and missiles were in the air at once. Does a microwave network hold up when the electromagnetic environment is just absolutely filthy with interference?
That is where the infrastructure less advantage really shines. In those saturation attacks, the goal of the adversary is often to overwhelm the sensors, but also to physically degrade the network. If you rely on a central fiber hub and that hub is destroyed, your entire regional defense goes dark. But with a microwave mesh, the network can be self-healing. If node A is destroyed, node B can often swivel its dish or use a secondary link to route data through node C. We saw this in the recent engagements where localized command and control nodes stayed operational even after major terrestrial lines were severed by long-range strikes. The resilience comes from the decentralization. You are not defending a single cable, you are defending a web of points.
It reminds me of what we discussed in episode 1193 about information attrition. The idea that you do not need to destroy every missile if you can just break the information flow that coordinates the defense. If the microwave links are the thing keeping that flow alive, they become the highest priority targets. I have noticed that in a lot of the hardened sites in Israel, they are starting to shield these microwave units in specialized enclosures that can withstand shrapnel without blocking the signal. It is a strange sight, these high-tech dishes wrapped in what looks like armor.
It is a necessity. If a drone explodes nearby, the shrapnel can easily pierce a standard plastic radome and wreck the electronics. But there is another layer to this that I find fascinating, and that is the integration with alerting systems. In Israel, the Home Front Command needs to trigger sirens and phone alerts within seconds of a launch being detected. That data often travels over these same microwave backhaul links. If you lose those links, you do not just lose the ability to shoot down the missile, you lose the ability to tell civilians to get to a shelter. The stakes for reliability are literally life and death.
Let's talk about the deployment side of things. You mentioned that you can set these up in an afternoon. In a dynamic frontline situation, say if the IDF has to move units rapidly, how portable are these fiber in the sky nodes? Are we talking about something that fits on the back of a truck, or do you still need a permanent tower?
It is both. For a long-term defensive posture, you want those permanent, hardened towers because height is your friend in microwave. You need a clear line of sight, and the curvature of the Earth eventually gets in the way. But for tactical use, there are mobile microwave trailers. They have pneumatic masts that can extend 30 meters into the air. You park the truck, level it, raise the mast, and use an automated alignment system to lock onto the nearest backbone node. Within 20 minutes, that mobile unit has a multi-gigabit connection to the entire military network. It is a game changer for mobile command posts.
I can see why that would be a nightmare for an opponent's targeting cycle. By the time they identify a command node and coordinate a strike, the node has already packed up its mast and moved 3 miles down the road, reconnecting to the microwave mesh at a new location. It is the ultimate move and shoot capability for the information age. But I have to ask about the downsides. We have talked about rain fade and line of sight, but what about the sheer cost? Is military-grade microwave actually cheaper than fiber, or is it just a different kind of expensive?
If you look at it through a narrow lens, the hardware for a high-end microwave link is more expensive than a few kilometers of fiber optic cable. But that is a false comparison. The real cost of fiber is the civil engineering. It is the trenching, the permits, the labor, and the physical protection. In a mountainous region like the Lebanon border, laying fiber can cost hundreds of thousands of dollars per kilometer. A microwave link might cost $50,000 for the whole setup, and it works the moment you turn it on. When you factor in the speed to mission and the lack of maintenance for a buried cable that might get cut by a landslide or a bomb, microwave is incredibly cost-effective for the military.
It is basically an insurance policy that pays out every single day. One thing that Daniel mentioned in the prompt was how we can see this through open source information. For the listeners who like to do their own digging on satellite imagery or ground level photos, what are the tells that a site is using this high capacity backhaul versus just a standard radio link?
Look for the dishes. Standard tactical radio uses antennas that look like whips or long poles because they are broadcasting in all directions. High-capacity microwave uses parabolic dishes or flat panel arrays. If you see a tower with multiple circular dishes pointed in very specific horizontal directions, that is a backhaul node. The size of the dish often tells you the frequency. A very small dish, maybe the size of a dinner plate, is likely an E-band link for short-range, high-capacity data. A larger dish, a meter or more in diameter, is probably a lower frequency link meant for long-distance hauls. In Israel, you often see these on the pillbox towers or at the top of reinforced concrete bunkers.
And the alignment has to be incredibly precise, right? If the tower sways too much in the wind, does the link drop?
It can. This is why military masts are built to much higher stiffness standards than your average cell tower. They are often guyed with heavy cables or built from thick steel lattice. However, modern systems also have electronic beam steering and mechanical stabilization. Some of the high-end units can actually compensate for a few degrees of sway by shifting the signal phase electronically, keeping the beam locked on the target even if the mast is moving. It is the same technology they use on ships to keep satellite links stable while tossing in the ocean.
That is wild. It is like a sniper scope that automatically stays on the bullseye even if the shooter is breathing heavily. So, we have this resilient, high-capacity, hard-to-jam network. What is the counter? If I am an adversary, and I know I cannot easily jam the beam, and I cannot cut a cable that does not exist, how do I degrade this network? Is it just a matter of physical destruction of the nodes?
Physical destruction is the most straightforward way, which is why the nodes are so heavily defended. But the other way is sophisticated electronic warfare that targets the handshake of the system. Even a directional beam has what we call side lobes, which are tiny bits of signal that leak out to the sides. If you have a sensitive enough receiver, you can pick up those side lobes and try to analyze the protocol. If you can inject a signal that mimics the system's own atmospheric compensation, you might be able to trick it into dropping its modulation or disconnecting entirely. But we are talking about nation-state level capabilities here. This is not something a small insurgent group can do with a modified walkie-talkie.
That brings us back to the Iran-Israel dynamic. We are talking about two very technologically advanced adversaries. Iran has a very sophisticated electronic warfare suite. Do we see a cat and mouse game happening with the frequencies? Like, are these microwave links constantly hopping between bands to avoid detection?
Frequency hopping is more common in lower bandwidth tactical radios. For these high-capacity microwave links, the strategy is usually power and precision. They use just enough power to maintain the link and keep the beam as narrow as possible. But the real evolution we are seeing is the move toward multiband systems. You might have a single unit that runs an E-band link and an 18 GHz link simultaneously. If the E-band link is jammed or heavy rain moves in, the 18 GHz link takes over the critical traffic without a single dropped packet. It is about redundancy within the wireless layer itself.
It is fascinating how this technology has matured. It used to be that wireless was the weak link in any network, the thing you only used if you absolutely had to. Now, in the context of modern C2, it is becoming the strong link because it is the only thing that can survive the chaos of a 21st century battlefield. I want to circle back to something we touched on in episode 767 about the nervous system of war. If the microwave backhaul is the nerves, then the command centers are the brain. How does this fiber in the sky change the way a commander actually makes decisions?
It enables what the military calls distributed command and control. In the old days, you had to have your commanders close to the front because that is where the wires went. Now, with high-capacity wireless backhaul, you can have your decision makers in a hardened bunker 100 miles away, but they are seeing the same real-time, high-definition radar data and video feeds as the guy in the foxhole. It removes the geographical constraint of the network. You can put your brain wherever it is safest, and as long as you have a line of sight to a relay tower, you are in the fight.
And that safety is key when you are facing the kind of precision-guided threats that are common now. If your command post is identifiable by a massive bundle of fiber cables snaking into a hole in the ground, you are a sitting duck. If you are just another node in a wireless mesh, you are much harder to pin down. Herman, what are the practical takeaways for people following these developments? If someone is looking at the defense posture of a country like Israel, what should they be watching for in the microwave space?
First, watch the infrastructure. The construction of new, hardened towers in strategic areas is a leading indicator of where a military expects to need resilient command and control. Second, look at the frequency allocations. When you see a military moving into the higher E-band and V-band ranges, they are preparing for a massive increase in sensor data, likely driven by things like AI-powered target recognition and multi-static radar. And third, pay attention to the failover events. In recent conflicts, when we have seen terrestrial networks go down, but the defense systems remain operational, that is the invisible success of microwave backhaul.
It is the ultimate silent professional of the networking world. It does its job, nobody notices it, and that is exactly how it should be. I think the biggest takeaway for me is that we need to stop thinking of wireless as a synonym for unreliable. In the right hands, with the right engineering, it is actually the most reliable thing we have when the world starts falling apart.
I completely agree. The physics are challenging, but the engineering has caught up. We are living in an era where the air itself is becoming a hardened data bus. What I find wild is that we are already looking at the next step, which is free space optics. Imagine using lasers instead of microwaves to send data between these towers. You would have terabit per second speeds and zero electronic signature.
Lasers in the sky. I am sure Daniel will have a prompt for us on that in about 6 months. It is the natural progression, right? From copper to fiber to microwave to light. The goal is always the same: faster, more resilient, and harder to break.
And that is the arms race. Every time someone finds a way to cut the cord, the other side finds a way to bridge the gap through the air. It is a constant battle between the backhoe and the beam.
Well, the beam seems to be winning lately, at least in the high-stakes world of missile defense. I think we have covered a lot of ground here, from the physics of rain fade to the tactical advantage of mobile masts. It really changes your perspective when you see a dish on a tower. It is not just a piece of hardware, it is a critical link in a chain that keeps millions of people safe.
It really is. And it is a testament to the ingenuity of the engineers who have to figure out how to make these things work in the middle of a dust storm or a missile barrage. It is one thing to set up a link in a lab, it is another thing entirely to do it in a war zone.
For those of you listening who want to see what this looks like, I highly recommend checking out some of the OSINT accounts that track Israeli defensive infrastructure. Once you know what to look for, those microwave dishes start popping up everywhere in the background of news footage and satellite photos. It is like seeing the skeleton of the network.
And if you want the foundational context on how these networks actually use that data once it arrives, definitely go back and listen to episode 767. We talk about the command and control side of things there, which is the what to today's how.
Good call. And if you are interested in the broader context of the current regional tensions, episode 1193 on information attrition is a great companion piece to this one. It really helps explain why the redundancy we talked about today is so vital.
The network that stays connected the longest is the one that wins. It is as simple and as complicated as that.
A perfect note to end on. Thanks for the deep dive, Herman. I actually feel like I understand why those little dishes are so important now.
Any time, Corn. It is a fascinating world once you look past the hardware.
This has been My Weird Prompts. A huge thanks to our producer, Hilbert Flumingtob, for keeping us on track and making sure the audio doesn't have its own rain fade issues.
And a big thanks to Modal for providing the GPU credits that power the research and generation of this show. We couldn't do these deep dives without that kind of horsepower.
If you are enjoying the show and want to make sure you never miss an episode, search for My Weird Prompts on Telegram. We post there as soon as a new episode drops, so it is the best way to stay in the loop.
You can also find our full archive and all the ways to subscribe at myweirdprompts.com. We have over 1,200 episodes there covering everything from quantum physics to the history of the donkey.
Mostly the donkey, if Herman has his way. Thanks for listening, everyone. We will catch you on the next one.
See you then.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from sloss